Kathy, it's great to have you here today. Kathy is an associate professor of chemistry and atmospheric sciences here at the University of Alaska Fairbanks. She's done studies. She has a degree from the University of California in Davis, where in 1990 she got a bachelor in science. She's also studied at the University of Washington, where she received a master's degree in 1994, and at the University of Nevada, Reno, where she received her PhD in 96. Kathy joined the Geophysical Institute in the fall of 1998. Her research focuses on atmospheric sciences, particularly aerosols and their impacts on visibility, global climate, ecosystems, and human health. Kathy's research includes laboratory experiments and field studies of atmospheric aerosols and their properties. She is currently investigating the sources, size, and composition of optical properties of particulate matter entering the Arctic from Asia and other continents. Kathy was a recipient of the 1996-1997 Fulbright Fellowship of the University College, Galway, Ireland. Kathy, it's great to have you here with us this afternoon.
Thank you.
And Kathy seems like a great person. You're going to love just all that she has to share. So thank you, Kathy.
Hi, everybody. Thanks for joining us. I'm really delighted that you guys all took time out to come listen to the mentor lecture. You hear a resume of a scientist. It sounds, highfalutin and really one of those things that it's impressive, right? The truth is, it really isn't that impressive. It's something that almost anybody can do. It's just a function of understanding science and enjoying it. And I have the best job in the world. I love what I do. I get to deal with students. I get to deal with science. So being a professor gives me an opportunity to work with students like you in the community, but also to work with graduate students here at the university and to do scientific experiments and do a bunch of different studies. And for me, I'm an atmospheric chemist. I study air pollution, how things move. A lot of the time when I'm doing the studies, I'm actually doing them in the Bering and Chukchi Seas. I've done measurements in Barrow. I'm down in Adak. So I get to do a lot of studies that are here in the state that are important to us. Now, some of you may have gotten an opportunity to do our Exploring the Senses hands-on activity. Did you feel the wind blow, in terms of touch? Did you see clouds? Did you see smoke? So you went through a bunch of the different senses and talked about what you felt. Did you see something? Did you feel something? Did you hear something? And as a scientist, when I go out and I listen and I see and I feel, I start asking questions. And that's the fundamental part of science, is you ask questions and then you try to come up with ways to answer them. And so for me, when I go outside and I hear wind go by, one of the first questions I might ask is, what is wind? What's moving? Why does it happen? I end up with a whole series of questions. And that's the first part of being a scientist, is you want to ask questions. You're curious. You want to know what's happening around you. So you take that opportunity and say, okay, so now I've got some questions. What can I do to answer them? And so we have a method we call the scientific method. And that's a highfalutin name for saying we try things, and if they don't work, we throw them out and try something else. And so what you do is you come up with a series of questions based on something you're interested in, and you say, okay, I want to answer this question. So for example, if I say I'm outside, it's a really pretty day in Fairbanks, we have some high clouds, I may say, what's a cloud? And, so I'm going to say, maybe I want to study something about this cloud. So the first thing I have to do is come up with some way of testing what I think is going on. So, okay, I've got a cloud. It's kind of white and fluffy. It looks a little bit white like whipped cream. I'm going to say my first hypothesis is going to be clouds are made of whipped cream. Okay, now what do? I've asked a question. I've proposed what I think is the answer. Where do I go from here? And I have to come up with some sort of test to test. Is the cloud made of whipped cream? Well, how could I test if the cloud is made of whipped cream? I could take a plane, go fly through it, take a sample of the cloud. I come down, guess what? Cloud's not whipped cream. So that potential, what we call hypothesis, my statement that the clouds are made of whipped cream, is wrong. Okay, I took that sample though, so maybe I know something from that sample. The sample is made of water. Clouds are made of water. Okay, so now I can ask a further question. If a cloud is made of water, how did that water get there? So it's a process of testing a series of assertions, a series of statements. Is this correct? and saying yes or no. If it's yes, I know something and I can take a further step. If it's no, I've also learned something. So being a scientist is just a function of asking a whole bunch of questions, coming up with ways of testing those questions, and then asking a new set of questions. And a lot of the time when you're dealing with science, you put in a lot of work. You collect a lot of data. You have, computers, you've got instruments, you've got all these complicated things. And you sit down and you look at all the results that came out, and your first thought is, what do I do? Because you've got this pile of data. And then next thing is you start piece by piece working at different little levels of it and starting to ask the questions and plot the data out, and you start seeing things in it. And some things will make sense. You look at that and say, oh, I know that the cloud is not whipped cream, it's made of water. Therefore, in this particular case, I can see from my data that it acts like it's made of water. That makes sense. I may also see something really funny. And a lot of science is based on gee, that looks strange. To give you an example, I recently, 2004, had an air sampler on a ship out in the Bering and Chukchi Seas. Okay, I've done this a million times before. You put the sampler on the ship goes and runs around, you come back, you take the sampler off, you take the samples, you go analyze them, the data comes back, and most of the time you can look at the samples and say, okay, I know that this air had this stuff in it at this particular point, and that makes sense. And periodically you hit something that is, gee, that looks funny. I'm in the middle of the Bering Sea, and suddenly I have what looks like sand in my samples, in the air. So I have sand in the air, in my samples, in the middle of the ocean. And that led to a, gee, that looks funny moment. And so I went ahead and I used some techniques I commonly use to try to figure out where air came from, using, maps like you see on television with, the meteorological, with the air moving. Had some maps like that, went ahead and looked at where this air may have been prior to getting to the Bering Sea. And it doesn't go near any of the sources I know put sand into the air. I'm thinking, boy, this is really strange. So I went ahead and worked it back, and well, the air came over the Kamchatka Peninsula of Russia. I happen to know there are a lot of volcanoes in Kamchatka. So in this particular case, I called up the folks at the Alaska Volcano Observatory and said, on this particular day, was there an eruption in northern Kamchatka? And they said, yes. How'd you know? And it turns out I had gotten smoke from the volcano, ash from the volcano, in my air sampler in the middle of the Bering Sea. The air had carried the ash plume out over the Bering Sea, and I had it in my sampler. And that was a really cool moment. That was one of those eureka type moments, it means I found it. And it was a really nice opportunity. It's one of those things that you start working through methodically and you come up with hey, gee, this looks funny, and then you go try to figure out what caused it. And that's what science is. Science is asking all these questions, coming up with ways of testing them, and then adding to the knowledge you have. So it's a lot of fun. And the big picture, how the world works, is how we understand how the world works is being put together by a whole community of scientists, all saying, hey, gee, that looks funny, or I wonder why. And it's a lot of fun to get involved in this because so many people have so many questions, and it's something that you can see every day. You can ask questions every day. I mean, I walk out in the morning, and I'm in Fairbanks, so I see the Alaska Range, across the valley. It looks beautiful. Maybe it's a little hazy. As an air pollution person, my first thought is, what haze is that? And that, is kind of the way I start my morning. Or I start my morning by looking out and going, oh, it's clear. Or, oh, it's cloudy. And starting with I wonder what it's going to do the rest of the day. These are everyday questions I ask. And it's the type of thing you guys can do at any point, is you can go out and say, here are some questions I have, here's the type of thing I want to do. And then you can, if you want to really become a scientist, or even just use science in your everyday life, ask the question, try to come up with some way to answer it. Come up with a statement that says, this is what I think's happening. Try to prove whether you're right or you're wrong, and then go from there. And you find that it becomes more and more natural the more you do it. And so scientists go through their whole lives asking, why? Why does it behave this way? Why am I seeing this? What's going on? And that's fun. I mean, because you're not bored. It's not a classic 8 to 5 job. You wake up in the morning, you're doing it. You go to bed at night, you're doing it. I mean, it's a lot of fun. Now, in terms of asking the right questions, all questions are good. The right questions can help you really get at the key things that are going on. So if you're going to be doing science, you want to be able to formulate your questions in a way that is testable. And that's hard. That's something that you're going to learn about during the next lecture, is how to set up these questions so that you can do an experiment and test them. Because if I go out and I say, why does the sun burn? That's a huge topic. I can't do all that in one test. This is something that scientists have been working on for years, and we've got a lot of information, but it's by people asking little questions that all come together to answer this big question. The aurora is a classic example. People have been doing research on the aurora for 100 years. And originally, we couldn't get up there. We couldn't make measurements in the aurora. So you had to come up with experiments here on the ground that would help you test what was going on up above you, because you couldn't reach it. And so you have this case where you start with the little questions and things that are testable that you can do right now. And then as you get more advanced, you start asking tougher questions. Because the easy ones have been solved, you have a base of knowledge, or your technology has advanced enough that you can do cool things. So with the aurora, we started with ground-based. Then what could we do? We could send rockets up. So you can take now rocket measurements. And so now you have more information. And then we got satellites up, and you can see it from a different angle. And that gave us more information. And we got computers, and we can do computer models now to try to figure out what's going on. And so piece by piece, we've been understanding the aurora more and more, because everybody started with what they could do, and then technology advanced and people did stuff that was more advanced. And that's the type of thing you do. So you start with a basic question, you test that, you find out everything you can, then you move to another question, usually that comes from your first question. And so you get this evolution, and a whole scientist's whole career will usually be asking questions about one specific area. For me, it's air pollution. I see stuff in Alaska that I know is not produced in Alaska. So my question is, where did it come from? And that, for me, is a lot of fun, because what do I need to do? I need to know what the sources of air pollution are, how the atmosphere works in terms of moving stuff around. Is this from the smokestack, just one village over, or is this from the one that happens to be in China? I need to know all these different sources. I need to know how things move. I need to know some chemistry. I need to know how things change. I need to know, can I see what it is? Can I analyze for it? So I basically get paid to do a puzzle. I have all these different little questions that add up to what I see in my air sampler. So I ask all these questions, I get all these different pieces, and then I have to put them together into a puzzle that works. And so I get paid to do puzzles. That's basically what scientists get. We get paid to do puzzles. It's a lot of fun. And we all have learned through trial and error what type of questions to ask. When I first started asking questions as a little kid, I would ask questions that there's no easy answer to. I would start with, why does the sun work? Now my father's a physicist. He could tell me a lot about it, but he couldn't tell me exactly how the sun worked. So I learned to start asking the smaller questions that led to the bigger questions and led to the overall understanding of what was going on. And part of what you should be doing in your science classes is this type of process. Start asking the questions. If your teacher doesn't have the answer, contact me. Contact some scientists. Start asking questions. What you'll find is scientists love to talk. All of us, big mouths, we love to talk. If you come and ask us questions, we'll do everything possible to help you answer those questions. We may know, we may not know, but we may know who to send you to. So if you came and asked me about earthquakes, I know a little bit about earthquakes. But if you asked a very specific question that I don't know, I'll send you to someone who knows about earthquakes. So there's a large bunch of people who would be willing to help. The other thing is you have access through the internet, libraries, books, to a bunch of this information. So you can start reading up on things you're interested in and start formulating your own questions. So it's a case where, with the science, you learn through trial and error what things we do know and what things we don't know. So you start off thinking, okay, when I moved up to Alaska, I thought I had a pretty good idea of what sources were impacting Alaska. I had read a whole bunch of stuff in my area about what was going on in Alaska. Figured I had a pretty good handle on it. Until I was looking at data from Denali National Park and Preserve, and every spring there's this spike in dust. Okay, Denali National Park in spring is covered with snow. We're not getting dust off the ground. It's under snow. We're getting dust from somewhere else. That was a, gee, that's funny moment. So there was something here. And so I started looking at what was going on. And so I hypothesized, this is not local. There was my statement. I did not think this was local. Now I had to prove, was that a true statement? So I went back. I looked at where the air came from. I looked at potential sources. I looked at papers people hadn't looked at since 1977. And what I found was, it wasn't from us. It wasn't from Alaska. It was coming from China. And it was coming every spring. So it was a case of my asking a little question about, why is this occurring? And trying to find out what was going on, and I found out my hypothesis was right. It wasn't local. It was coming from China. But it was one of those things where you thought you knew it, and you got that, gee, that's funny moment, and you set up your hypothesis. I was able to test it and say, yes, this is correct. It's coming from somewhere else. That's the way science works. I've published a bunch of papers on that now. And so now a bunch of other people also think it's not from here, it's from China. So it's a case where one scientist comes up with a, gee, that's funny moment. And now other people are quoting me and using my work to say, yeah, look, we've got the stuff in Alaska. It's not from here. And then you work on what that actually means. So start with the small questions and then work your way up. And you'll find it's a lot of fun. And when there are times you're likely to ask questions, anytime. Doesn't matter when. Okay, maybe in the middle of mass might be inappropriate, but you know, it's one of those things where ask questions, constantly ask questions. Ask your teachers, ask your parents. You know, search stuff on the internet. Always ask questions, and you'll be a great scientist. And you'll find that you too will have those moments of, gee, that's funny. You know, I wonder why. So if you happen to be at the beach and suddenly, you know, there's a big wave, why was that wave big? That's a moment for a question. You know, that's my question. Why was that particular wave so big? Or why was this particular storm so strong? I mean, you guys had a spectacular storm on the west coast of Alaska earlier this year, right? Spectacularly big storm. Why was that storm so big in particular? Every day you have the opportunity to ask questions, and you should take full advantage of it. And once you've asked those questions, then you can start setting up the what statements are going to describe what I think is going on, and how do I test them. So you're going to keep doing this process over and over again, and you're going to find that it becomes easier with time. And it's the case where your teachers can help you, but it is the first step on the whole road to science, is asking the question, why? And keep asking. And you'll find it's a lot of fun. So with that, I'm going to go ahead and turn this back over to Hal to see, do you guys have any questions for me?
We want to come at so windy here in Shishmaref.
Why so windy in Shishmaref? That question. If you look at the globe and you look at the meteorology, how the air is moving, you find that there are certain areas of the world where you tend to get really deep storms, and one of those areas is in the Bering Sea. And so it impacts the west coast of Alaska. So you guys are right in the prime area where you're going to get these big storms coming through on a regular basis. And with those storms, you've got a lot of air moving, and that, of course, is your wind. So when you've got a deep pressure system, if you watch the news, they'll talk about your low pressure. You've got air moving around that low pressure, and it brings those winds right into Shishmaref. So you guys are right, bullseye for these really strong winds as this air is moving around this low pressure. So you guys get a lot of wind, and you don't have any mountain ranges to divert it. If you happen to, have a case where you've got the flat ocean, so it comes in nicely. If you don't happen to have the flat ocean, you're right behind a mountain range. The mountain range can move the air in such a way that you don't get hit by the wind. But when you've got the water, a flat surface, that wind has nothing to stop it. And as a result, you guys get some really strong winds.
The question we have is, what inspired you to study the air?
What inspired to study the air? To be honest, it was my dad. My dad also does air pollution work. And he was one of those great scientists that you could always ask questions of. And so I started asking a bunch of these questions, and he'd answer me. He had the answers for most of them, and periodically I'd hit one where I had him stumped. And so I would ask questions and then work with him, and it was a lot of fun. And he was really excited about what he did. I mean, we'd go put air samplers in national parks around the country. So when we went on family vacations, we didn't have a lot of money. We couldn't fly. So we had a car. In lower 48, you can go a lot of places with a car. So we'd load up the car with the whole family and a bunch of air samplers in the back. And we go put out these air samplers. So I learned by watching him how to figure out where to put a site. And he taught me a lot about what was in the air. And I really enjoyed it. And he was really enthusiastic about it. He loves to teach. And so as a result, I got really excited about it. And I've gotten into it. And, I mean, some of my earliest memories, Mount St. Helens started erupting in 1980. And it was doing little puffs. So you'd see this beautiful ice cream cone-shaped mountain, and you'd see this puff of ash come out. And, having grown up in Northern California, we didn't have anything that exciting. And, of course, it impacts the air quality. So my dad went to go find my mom, who was in law school at the time, and said, Mount St. Helens is erupting. And Mom said, so when are we going? So we piled the whole family in the car with 4 air samplers, drove up to Mount St. Helens, and Dad was looking for sites around the mountain to put air samplers. So we were putting samplers around the mountain, and you'd hear this boom, and the ground would shake, and you'd look over, and there's ash coming out of the mountain. It was really cool. I mean, this was a lot of fun. And that was one of my first memories of working with Dad on terms of air quality stuff. And then, of course, the mountain really blew in May of 1980. 2 of Dad's air samplers are still buried at the mountain. One of them was upwind, and the other got such a nice sample, he made a really prestigious scientific journal. So, I mean, it was one of those cases where we did something that was really fun. And that's what got me into science. I mean, I really enjoyed the questions, and he was really excited, and I loved it.
Yeah, we're wondering how the dust might affect the sea ice.
How this affects the sea ice? That's a really good question. And to be honest, it's one scientists don't know the answer to yet. So that's a really good question. You can get money to do research on that one. The dust, we know, comes across in spring and lands on the sea ice. And it changes the color of the sea ice. You guys see this, right? You get some brown on your sea ice in spring. Well, that changes how reflective that ice is. And so it's going to reflect light back to space. And so it's going to cause a cooling right on that surface in terms of, it keeps light from getting scattered back to space. So what you've got is a case where you're getting more of the sun's heat absorbed by those particles on the ice. And so that will help the ice melt faster. If it was pure white ice, it reflects really, really nicely. And so that heat doesn't stay there. The sunlight gets reflected back, right? You can get a beautiful sunburn when you're on the ice, right? So in this particular case, by putting this brown layer on the ice, you help the ice melt faster. And so that dust is having an impact on the ice. And then, of course, if the ice is melting earlier, that has an impact on the fish and the animals and other things that are going to be in the area. So that is a really good question. I mean, we don't know, we don't have the absolute numbers. We have an idea, but we don't know for sure, here's how big the change is. So that is a really good question.
Where did the ice come from?
The ice come from? Ice is cool stuff. as you know, it's frozen water. And it's a case where we're really lucky to have water at the temperature we have it on Earth, because it can be in a gas phase, so you feel the moisture in the air. That's water. We have liquid water, and then of course we have ice. And what happens with ice is you get water really, really cold, and the water molecules line up into a lattice. Basically, they crystallize. So imagine a diamond. The molecules are perfectly ordered. The same thing happens with water. Water, when it gets cold enough, the molecules form this really pretty structure that is hard. And that is going to be your ice. So basically, as the water gets colder and colder and colder, the molecules rearrange until they can form a perfect, structure where you have the molecules interacting with each other, and each one is an even space apart. So you end up with a really nice, trying to think of a good example of what it would look like. If you have Lincoln Logs, for example, or Tinker Toys, and you stick you've got two balls and you stick the poles between them. If you go ahead and do squares on top of squares, so you have all these cubes, that's what you're looking like. That's what the ice molecules end up doing. They end up forming cubes. And you end up with something that's very strong and very cold, of course.
Where does from China come from?
Where does from China come from? It comes from the Gobi and Taklamakan deserts. If you know that Mongolia is just north of China, there's a big desert in Mongolia called the Gobi Desert. And it gets big dust storms in spring. And so these high winds carry a lot of dust high in the atmosphere. So it crosses the ocean at around 9,000 feet for the most part, but in the process of crossing, some of the dust falls out. And it falls out here in Alaska, and it falls out on glaciers. There's some really nice cases where you have dust actually falling out at approximately 12,000 feet on Mount Logan in Canada, where you actually will end up with a brown layer of snow from the Asian dust. But it's dust from the Gobi Desert, and sometimes you'll get it from the Taklamakan Desert, which is in southwestern China. But for us, most of the time when it hits Alaska, it's coming from the Gobi Desert, and it's with those big dust storms in spring. They take the dust, they carry it up, it zips across the Pacific. You can go from the Gobi Desert to Adak Island in 4 days with the dust cloud. And that is moving very, very quickly. For the atmosphere. It's a really neat phenomena, and people didn't know that this dust transported until approximately 1998. So this is something that is now a big area of science, studying the dust transport from Mongolia, basically, into Alaska, Washington, Canada, Oregon. You see it down in California, you see it in Hawaii. All these different places get impacted by it, but it's a brand new field of science, and there are a lot of studies going on right now to try to figure out why the dust gets picked up when it does. I mean, they know that it's due to big meteorological events, but what causes them to occur right then is something that we're looking at.
What forms snow?
What forms snow? Snow, like ice, is water, but it's water that's freezing in the atmosphere. And most of the time when you get snow, you've got some particle that's in the atmosphere, and water, when it gets cold enough in the vapor phase, is going to do what we call condense. Basically, water molecules stick all over your little particle. And the particle then starts to grow because these water molecules are all stuck on the surface. And as you get more and more water, it continues to grow until a point where you start seeing it visually. You can see it with your eye. Now you have all sorts of different funny snowflake shapes, right? You guys know that you have needles, you've got flat hexagonal plates, you have really pretty, what we call dendrites, that are the classic snowflake that everybody cuts out of, paper, with all the different legs on it, with the different structures. All of these snowflakes form at different temperatures. It's a function of how fast the water molecules are being added onto that initial particle determines how fast it's going to grow and what shape it's got. So if you go outside and you have those perfect 6-armed snowflakes, the classic ones. Those form at about minus 14 degrees Celsius, so close to 0 degrees Fahrenheit. So it's a case where by having it grow more slowly and at that temperature, you can get those beautiful structures. Whereas if you're growing needles or straight hexagonal plates, those will grow at other temperatures. So what happens is it's just a function of you start with something and the molecules of water start attaching to it because they want to stick to it, and then they start growing and you end up with the snowflakes.
Has the water been rising?
Has the water been rising? The consensus among most scientists I've talked to is yes. Not a huge amount, but they do think water is rising, and it's due to a couple different things. One thing is when you have glaciers on land and you melt the water, that water will end up in the ocean and will lead to a sea level rise. The other thing is as oceans get warmer, as water gets warmer, it expands. Things that warm up tend to expand. Water is no different. So the water in the oceans is actually expanding a little bit. Is it a very big sea level rise yet? No. Is it something people are concerned about? Yes, especially people who are in coastal communities, because it doesn't take much water rise before you start having bluffs wash away or you have flooding along the coast. So the sea level is rising, but it is not a lot yet.
What causes seasons?
What causes seasons? Seasons is a function of what portion of the earth happens to be closest to the sun, and the earth goes around the sun in a way that it's not a perfect circle. If it was a perfect circle and the earth always rotated perfectly vertically with respect to the sun, we would have no seasons. But as it is, the earth goes around the sun in what we call an ellipse. So it's not a perfect circle, it's an oval, it's almost egg-shaped. And when the earth is closer to the sun, it gets warmer, and when it gets further away, it's a little cooler. And then, of course, the earth tilts. And so if we're tilted towards the sun, and we happen to be near the sun, we're going to be warmer than when we're tilted away from the sun and we're further away from the sun. So this tilt of the earth and where we are in terms of how close we are to the sun determines the seasons. So we have a case where, during summer, we're going to be towards the sun and we're getting warmer, and then when we happen to get rotated away, we're going to be a little bit cooler.
How long have you been studying the air around you?
How long have you been studying the air around me or overall? I mean, in terms of here in Alaska or...
Overall.
I started formally working in air quality in 1986, so 19 years. I started between my senior year high school and my freshman year college. So I've been doing this a long time. In terms of studying air, specifically in Alaska, I've been doing that for 8 years now.
We have a student being shy, but he wants to know, he was the one who was wondering about the sea level rise. He was wondering how fast it is now and how fast it might be in the future. I know that's out of your area of expertise, but we're hoping you would know.
It is my area of expertise. Right now, I think it's on the order of centimeters, and that's probably been in the past 50 years, so not very fast. There is some concern that is actually getting faster. So how fast, I don't know. There doesn't seem to be agreement about how fast this is actually going to occur, and it depends on a bunch of things. It depends on how hot we get in areas that have the ocean. It depends on, do we melt, for example, the Antarctic ice cap? If we do, or Greenland, most Alaska glaciers, etc., then we're going to be putting a lot of fresh water into the system, and the sea level rise we would expect to get significant fairly quickly. But it depends on how fast we've got heating and cooling and all these other things occurring. So in certain areas, when you talk about global warming, the truth is the whole globe on average warms, but certain areas will get warming and certain areas will get cooling. If the areas that get warming happen to be areas that have ice and we get a lot of melting, then you would expect to see the sea level rise go up fairly quickly as that warming increased. But if the areas that happen to have the ice were actually getting a little bit cooler because of changing weather patterns, then you wouldn't see it go up as quickly as you would expect. So right now we really don't know how fast this is going to occur. But I mean, it's a very important question, and it's something that if you're interested in, you could probably make a really good career studying that right now.
Why does the Earth rotate?
Why does Earth rotate? That's a really good question. That is a really good question. This is called Stump the Scientist. It has to do with how things were formed and gravity. And planets, as they form, they're kind of clouds of gas, and they may start off kind of uncentered. They're not perfect spheres. And so they're kind of wobbling, and as the gravity is kind of pulling them around, they're going to go around, and as a result, eventually they kind of smooth out, round out, get formed, and you end up with something that has that rotation maintained. There are planets that go around the sun that don't actually, not necessarily the sun, but other solar systems around other suns where the planets don't actually rotate, or they rotate very, very slowly compared to what we have. As it is, we rotate, we do 1 lap per day. A lot of other planets will go slower than that. It takes a much longer period of time for them to have a day. And how that rotation gets formed, it's a function of how that planet was formed. Did it get caught as it went by, or did it get formed, from a coalescing piece of matter around the Earth? It's not an easy thing to talk about to some extent, because we can't make planets. We don't just go up there and go, boom, there's a planet. We can study it right then. We have to look at a whole bunch of different planets and see planets forming in the sky and try to figure out from there why we see this rotation and we see other things happening. It's a very complicated thing. It's a great field to study, and because we have better satellites and other things now, and like the Hubble Space Telescope, things along those lines, we're getting a better handle on these things. We can watch it happen more frequently. We're seeing planets in other solar systems. So we're in the process of learning how all of this comes together. But it's a really good question.
Their question was why we've gotten so little snow so far this year. We've only really had one decent snow, and this wind's taken it all away.
Yeah, we've got the same problem in Fairbanks. We have almost no snow. You get seasonal variation from year to year in terms of what occurs, how much occurs, etc. And it has to do with how the high and low pressure systems, the meteorological systems, set up any given year. And so in this particular case, we've gotten strong storms, but they've been warmer than normal. So we haven't gotten the snow that we normally expect. So in the particular case of Shishmaref, if you get a storm in and it comes a little bit further north than it normally does at this time of year, you're going to get the strong winds and you're going to get warmer temperatures, and you're not going to get the snowfall you're used to. If it comes a little bit south, like it normally would in fall, then what happens is you're on the cold side of that particular storm. You're getting some of the moisture pumped up, but not the really warm air. And when that happens, that moisture freezes, you get the snowfall. So a slight shift in the north to south, where the center of that storm is going to have a big impact on whether or not you're going to get snow or you're just going to get wind and rain. And Eric Stevens, who's going to be giving the lecture, the next mentor lecture, is actually a meteorologist for the National Weather Service. And he'd be a great person to actually give you the how normal is this. He knows kind of the statistics about, is this a normal fall, is this not a normal fall. From what we've seen here in Fairbanks, it's not a normal fall. We've had almost no snow, and then promptly it got cold. We're finally back up to normal, which is actually kind of nice. It was 14 yesterday. But it's a case where a slight shift in a meteorological pattern can have a major impact on what you actually see on the ground. And the fact that you are observing enough to know that you don't have as much snow this year, etc., that right there says that you are, doing the observations a scientist would do. And if you were to keep track of this year to year to year, you'd have what we call climate. Because climate is over all these years, what do you expect to see? So a slight shift can have a major impact, and it's a really good question as to why this particular year the pattern has set up a little bit differently. And that's one of the things climate dynamicists and weather personnel are trying to figure out. It's a good question. And thank you all the students. It was great to talk to you.
Here, I was just trying to show the students a picture from the National Weather Service where the center of the low was that was causing all the wind.
Okay.
Surface map they have.
And did you find the surface map?
We're to load up the image.
Okay. Yeah, and the way storms work is the winds go counterclockwise around the low pressures. So what you'll do is you'll find you've got that low pressure center, and then the winds are coming up around, and the moisture is at the front of what we call the cold front. So you're going to have a case where you've got the cold front and you've got the rain in front of the cold front, and you've got some along what's called the warm front, some along the cold front, but where you get the strong winds tends to be where you've got the cold front. It's your division between warm air and cold air, and you get those strong winds coming in, and this front is moving counterclockwise and bringing the air in with the strong winds behind it. So when you look at the surface image, once you get it, you can find the low pressure, you can see the clouds, and you'll be able to tell where the strong winds were.
I got maybe a little bit of an obtuse question.
Okay.
I sometimes like to teach kids a lot in terms of kinetic theory of molecules, not real quantitatively, no Maxwell-Boltzmann distributions or anything, but just in terms of the kinetics of molecules. In terms of those highs and lows, how would you best describe to kids, just in terms of the kinetics of the molecules, how the air from the high pressure is actually moving into the low pressure?
With air, you've got high pressure, which means you've got a lot of air stacked up, and you've got a low pressure where you don't have much. So the molecules are going to try to go from the high pressure to the low pressure. So they're going to start going down the gradient. Now, as they go down the gradient, the challenge is what we have is the Coriolis force, which causes things to spin, right? So as it's going from the high towards the low, it's going to change direction. So the air molecules don't end up flowing directly from high to low. They end up flowing between the two, perpendicular to the line between them. So they kind of go down and twist, is basically what happens. And that's where you get the wind. You get the wind where you've got the strong gradient, because the molecules are trying to get from the high pressure to the low pressure, but the Coriolis force on the Earth causes that shift. So you actually end up with the molecules moving clockwise around the high, counterclockwise around the low. And it's a function of you're trying to go down gradient, but you've got a case of the Coriolis force takes the molecules, because it's taking them so long to move, it has time to act and cause it to actually spin. So the molecules are moving. They're going from high to low. It's just that they get sidetracked.
The ice form later each year.
Why does ice form later each
Can you
year?
hear me?
That's a good question, and one that scientists are to understand, because it fits in with the concepts of global warming. It also is a case where we're trying to model it and we don't necessarily have it quite down. Warming later. If you have a case where, for example, you've got a global warming occurring, and you've got warming occurring over the Bering and Chukchi seas, the water is going to be warmer, and it's going to take longer for the air temperature to cool off that warmer water. So the ice will form later. So it'll require a longer period of colder air over the water to get rid of that extra heat. Water holds a lot of heat. It takes a lot of energy to get a pot of water to boil. It takes a lot of energy to change the temperature of water 1 degree. In fact, the unit of calorie, not the type of calorie you eat, but 1/1000th of that amount of energy, is what it takes to heat 1 gram of water 1 degree Celsius. It takes a lot of energy to actually heat water. So when you're trying to cool the water off, you're trying to pull the heat out of the water. And that takes a longer period of time because the water can hold so much heat. So until you get the heat out of that top layer of water, you can't really get the ice to start forming. So if the water is warmer, then the ice won't form as quickly. And if the air temperatures happen to be warmer, then you're not going to get cold enough to get the ice to form until later. So if you're observing the ice form later every year, that would imply that you've got something in there that you've got a warming occurring. Because if it was a cooling, your ice should be forming earlier every year. But what you're seeing is that it's forming later. That would be consistent with some sort of global warming type scenario. And whether or not that's a normal process and we're just in a great big natural cycle, or it's directly due to global warming, is something people are debating. Most scientists agree global warming is occurring. How quickly and how much of what we're seeing right now is due to the warming due to what humans are doing to the Earth versus how much is a natural cycle, that is being debated. So it's just the magnitude that's being debated, not whether or not it actually is occurring.
What do we do that cause global warming?
What do we cause as global warming? Global warming is, the way it's being discussed, it has to do with gases that we have put into the atmosphere that are really good at trapping heat. So it's, for example, if we burn coal, we produce a lot of carbon dioxide. Carbon dioxide is a great gas. It's like putting a warm blanket on the Earth. It helps trap the heat coming off the Earth in. So instead of it being radiated back to space, which would cause the Earth to cool, it's trapping that heat in to warm the Earth. So by putting out gases like carbon dioxide, we're helping trap the heat, which is causing the Earth to warm. That's the fundamental what we do to cause global warming, is we put gases into the atmosphere that are causing the warming. Now, we also do cause a little bit of cooling, too. When you put some particles in the air, they can scatter light back to space before it actually gets low in the atmosphere, and that will cause a cooling, because that energy is not now making it all the way to the Earth's surface. So that is occurring in some places. So you've got this warming due to the gases trapping the heat, and you've got a cooling due to the fact you've got these particles scattering light back to space. So you'd think, oh great, we should add more particles to the atmosphere. The problem is that most of those particles are the things you don't want to breathe. So they're, smoke, they're various pollution. You go down to, say, Los Angeles, California, it's got this horrible reddish-brown smog. That's the type of stuff I'm talking about. You really don't want to be breathing it. It's not very good for your health. It actually can help cause acid rain. So in terms of the adding particles to the atmosphere to combat global warming, that's not really a good option. So what you'd have to do to prevent the global warming would be to reduce our emissions of the various gases that could potentially cause it.
When you were saying about we're trying to see what the natural cycles are and if we've actually left those natural cycles with anthropogenic from human causes, I thought the prevailing attitude at this point was, from especially the 400,000 year record of the ice core, is that we've been pretty much able to discern what the natural cycles have been over the last 400,000 years, and that the data is looking pretty clear in showing that we've actually gone beyond those cycles now, and that our warming at this point is statistically significant in terms of it being above what those cycles have shown for 400,000 years. The so-called hockey stick, which gets so much attention in the press, the hockey stick curve. But isn't the prevailing attitude amongst climatologists that we are actually out of the natural cycles, which we do understand pretty well at this point? Of course, there's a lot to be learned, but in terms of what we've been able to learn.
I was going to say, my opinion is that we are way beyond. Unfortunately, there is still some discussion about what the natural cycle is versus what we have. And it's something that is being debated. Because a lot of people will say, yeah, I mean, we're beyond what a natural cycle has done before, but of that, is it a natural cycle plus this little bit of anthropogenic, or is it a low part of the natural cycle plus a whole lot of anthropogenic? And so trying to tease out which portion is attributable to what is where the debate is. And there are some scientists who fundamentally still don't think that we've really exceeded the natural cycle by a whole lot. That we've had quick warmings and coolings before in the past in the ice core record. And so that we're just in one of the warm phases right now, and we shouldn't be worrying too much. I think that most of the scientists would agree with you in the hockey stick theory is we are well beyond what a natural cycle would be. But there have been some significant warmings and coolings in the ice core record, and the naysayers point to those and say, look, we're not outside of what the basis is. There is still discussion on this. It is currently being argued.
Okay, now we get science and society sort of issues. If we're good scientists, we always have a great degree of uncertainty. In fact, we try to maximize our uncertainty so we don't make mistakes, and that's really good about how science works. That being said, we're obviously faced with some really critical issues of what's impacting humanity, and this region being one of the worst in terms of our dependence on sea ice, especially here in Gamble. Without sea ice, they lose their walrus and bowhead hunting, and that really is the only reason people have lived here for hundreds of years. In terms of the global warming, there's a time lag because the ocean and the land, so you get the terrestrial and the marine thermal mass, it's absorbing lots and lots of heat. We actually stop the process of the heating. If we can actually cut back on greenhouse gases, then you also have an equal number of decades for the cooling. So a lot of people are saying at this point that we really need to have an insurance policy where we actually stop the cause of global warming, even with the uncertainty. And that also, regardless, is that even if that isn't happening, the world needs to go to renewable energy anyways, because we're going to be running out of fossil fuels as we see the price of oil going up so dramatically lately, that it would be a good thing to do anyway. Do you have any comments on that?
I agree completely. In terms of global warming, we are the canary in the coal mine up here. We're the ones who are going to see the impact first. It's going to be most dramatic up here. And I believe fundamentally we're seeing it. And it is going to impact the way people are responding up here. In terms of how much damage has been done, it's going to take a long time to reverse the effects of the carbon dioxide we've already put into the atmosphere and the other gases. And there is a humongous lag. And you're right, the land and the water contain a tremendous amount of heat. There is a lag between there, etc. The ocean takes up carbon dioxide. What happens when we exceed its capacity? We have a bunch of issues there where we've already, in my opinion, made a change in we need to stop basically cold turkey to some extent in terms of producing these things, because right now, if we are, as we both believe, out of that natural cycle, it's going to take a long time before we come back down into that natural cycle, given how much stuff we put into the atmosphere already. In terms of renewables, we have to go that way. We have the foreign dependence on oil. We have gone to an interesting image here. The foreign dependence of oil and other renewable resources, we're going to be limited. We really should be looking at renewable resources. And Alaska has a lot of potential for things like wind. I know if you're talking about along the Bering Strait, wind could be a great one. We definitely need to move away from fossil fuel types of oil to things that are more renewable, sustainable, and don't put as much stuff into the atmosphere to keep that global warming continuing. I'm a firm believer in we should really look at energy conservation and other things to protect what we have in terms of the environment.
How does the snow form?
Snow form, it's a good question. In terms of snow forming, if you've got particles in the air and you've got very cold air, what happens is the moisture in the air wants to form something. So it sees a particle and you get these basically individual water molecules sticking to your particle. It's easier to stick to the particle than to stay in the gas phase. So you keep adding on particles of water molecules onto your particle, and your particle gets bigger and bigger. And most of what it becomes then is water, because as you grow it, more and more water is going to go to it. And so these particles will turn into snowflakes as more and more water joins it. Now, what shape that snowflake has depends on what temperature everything forms. So you have a case where if it's, say, minus 14, Celsius, you will have a beautiful six-armed snowflake. That's the temperature they form at. You can have another temperature where it gets colder than that, you may form a needle. So how the particles actually sit on the various particles, how the water molecules go to them, is going to change shape depending on what temperature you're at. And they're going to try to do it in such a way that you have, it takes the least amount of energy to actually stick on. So you're going to keep adding molecules until you actually end up with a fairly large snowflake or crystal or column, whatever it is. But you have to have it be very cold, and you have to have moisture in the air for this condensation, for the water molecules to actually stick to the particle.